Hey, this is David Rankin with Rankin Studio. I'm here today with a new tutorial. It's been a while, I know. I'm hoping you guys find the stuff I post useful. Today I'm going to be talking about how to do astrometry. So you're at the point now, where you might have a nice telescope, a pretty nice mount. You're getting good tracking on your images, nice round stars, 5-10 minute exposures, and you start thinking, what if there's an asteroid flying around in my pictures? How am I going to know that? If there is one flying around and I find it, what do I do after that? How do I identify this asteroid? If it doesn't have an identification yet, if it's new, how do I report that? So these are questions I had for a long time, and it wasn't until recently until I kind of dove into how to do all this stuff. And it's kind of important because you might be going through your images and find a moving object that ends up hitting the Earth and killing a bunch of people. So it's a real thing, and the more people that we can get out there covering the night sky, the better. There's a lot of space out there to look through, and these objects are moving around all the time. So it's important, if you are interested in this at all, to contribute to the science. So hopefully through this tutorial I'll at least put you on the right track where you can get your images, even images you may have archived, go through them, look for moving objects, take measurements of the moving objects, report them, get some practice with it, and get you acquainted with how the process works. So here we go. Before we can kind of get going, there's some software you need to get your hands on and get acquainted with. The first piece of software that's really important that we're relying on heavily is Astrometrica. I think it's around $50 United States currency, US dollars, but it's worth every cent. It's an awesome program. With this software, you can plate solve your images and take detailed measurements of moving objects in your images and import all known moving objects that would be in your images. So it's essential to our operation here. With these measurements we get, you can then go to Find Orb, which is Project Pluto, download the latest version of Find Orb, and you can generate orbital elements from those measurements, which you can then import into Stellarium or another planetary software, so you might be able to find your object down the road. So if you're going through images that are older and you find something new that's not coming up as a known object, this is very critical if you want to have any hope of finding this object again to get follow-up measurements on it. So I'll be going over that. AstroSurf has Iris. Awesome little program, freeware. There's probably many different ways for doing this. I'm sure you have your own method for calibrating your images, but I'm going to use Iris today. It's very, very easy, very quick way to calibrate images before you blink them to look for moving objects. This one is also important. Thinkman.com. He has some software called Dimension 4. And what this does is it synchronizes your system time on your computer with the universal time servers, it's very critical to do this before you go out and take images. So for future reference, you want to run D4, and it's running through all these time servers, and it's making very slight adjustments to your time in your system. So many tenths of a second, and excuse me, this is critical when you're taking pictures and finding objects, because in space you have to have your coordinates for your object, but you also need to know exactly what time it was there because it's moving, and if you don't know what time it was there, it's pretty much useless. So the more accurate you can get your system time to universal time, the better. And so you should make it a habit if you're going to be trying to do any kind of science with your images, to make sure you have extremely accurate time attached to your images. So I would definitely get your hands on Dimension 4. Also freeware. Go over this website as well in detail. This is Minor Planet Center's site, Guide to Minor Body Astrometry. There's a lot of detailed information in here you're going to need to know if you want to make measurements, formats, all that good stuff. So what I'm going to be doing is helping you get to the point where you would need this information. Where you actually find your objects, take measurements of them. This is very important information in here. They want images that have measurements that are extremely accurate, and so and there's a very, like I said, specific format. So make sure you get very acquainted with this page. before you send anything off to them, because they don't appreciate it when you do that. And I know that because I did it. Stellarium, Planetarium software I really like. We'll be using this software to import, an object. It has telescope control and all that stuff, so I use it for, my go-tos on my scope when I'm out imaging. You can generate orbital elements, bring them into Stellarium, and then find the object in the future, which is very handy if you accidentally stumble across something a few nights previous, after the imaging session, and you want to be able to locate it again. You can use Stellarium to get out there and do that. This is the format it needs for that. We'll go over that. But you also need to know the right ascension and declination J2000 coordinates for your object. So there's a few different sites you can use for that. Simbad is one that I use, just a database of objects where you can look up the right ascension and declination, because you'll need to input that into the plate solving software to give it a hint to where to look for where you took your images before you plate solve them. I'll go over that. Another place you can do that is also Astrometry.net. Very cool website. Doesn't always work perfectly, but we'll be trying it out. Okay, so here we're going to get started looking at a set of images I took from NGC 772 the other night. My light frames and my dark frames. Okay, so the first thing we're looking at here is we don't need to animate the entire set of images to look for a moving object. And you can see mine aren't exactly sequential because I had some bad frames and it renumbered it weird. I think sequence generator for that. Probably, again, user error though. So what I'm going to do is I'm just going to grab, every fifth frame. So 1, 5, 10, 15, 20, and 25. Worked out. Okay, so now I'm going to go into my Iris working directory, which I'll show you how to make. And I'm going to drop these 6 images in here. Then I'm just going to rename them to C1, C2, C3, C4, C5, and C6. Okay, so now I have a sequential set of images. I didn't lose any information. The FITS headers have all the time and exposure information. I just renamed them. Didn't do any. It's not a destructive process. Then I'm going to grab my dark frames. And then these ones are sequential, so I don't have to worry about renaming them. You can see they go 1, 2, 3, 4, 5, 6, 7. So that's good. I'm going to drop them into the working directory for Iris. I'm going to fire up Iris. And Iris is awesome, just so you know. So we got to calibrate these images now. So the first thing you have to do in Iris is set up a working directory under Settings. So you can see File, Settings. And I have my working path set up on my desktop to Iris W, which is the folder I just dumped all these image frames into. So make sure you set your working path before you get started. And if you're running a DSLR, you have to tell it what camera you're using too. There's great tutorials out there on setting up Iris to work with DSLR images. I'm using a CCD, and the software I was using to capture was Sequence Generator Pro. So it actually writes all this very important information to the FITS headers of the files that it captures, which is very handy when doing this kind of stuff. If you're using a DSLR, I'll give you some hints and tips to get there, but this is mostly CCD stuff that I'm going over right now. So pre-processing, we need to make an offset, but I didn't take any. That's your bias frame, by the way. I didn't take any bias frames, so I'm gonna go. I'm just gonna load up one of these frames, and fit to window. Then I'm going to open up the command prompt here in Iris, which is this button here. And I'm just going to fill 50. And I just filled it. It didn't add any information. It just filled it gray. So I don't want it. Pretty much what I'm saying is I don't want a flat frame or a bias frame because I didn't take any. So this is going to have it's going to have a neutral effect. It's going to have no effect on the image, but it still needs it to calibrate the images. So I'm going to save that out as to the same directory, Iris W, flat MA for flat master. Okay. Now make it dark. See, now for the darks, it wants to know what the offset image is, or the bias image I just made, which I named wrong. That wasn't supposed to be my flat, but it can be my flat because I'm going to do the same thing. I don't want any effect for my flats or my bias, so I'm going to do the exact same thing, and I'm going to call this bias MA, because I don't have any bias frames. So now for the dark, make a dark master. So you're making master frames from stacks, okay? So because I didn't have any bias or flats, I didn't have any stacks to make. I just made pseudo ones. I made fake ones. So the generic name for my darks, I will grab in a second. The offset image is going to be bias MA. The number of darks I had was 7. And so if I look at my Iris working directory at my dark files, you can see it's target set 2, 240 seconds. I'm gonna make sure that's the right frame here. Hold on. Make sure those aren't light frames. I might have grabbed the wrong ones. Nope, that's a dark frame. Okay, that's good. So again, back into here again. Make a dark. Generic name is going to be everything before the sequence number here. So target set 2, 240, 1 by 1 frame. Then it's going to look for the 1, the 2, the 3 in the software. So I'm going to just paste that into here. Call this again bias MA. Call this 7. And then do median stack on my dark frames. So now what it's doing is it's stacking my dark frames for me. Okay, and it did that. It's now I have a master dark. Before I can save it, I have to do a find hot COSUM command. Not sure what it does. I don't know exactly why they call it that, but it finds all the hot pixels in the image. So you can see all my hot pixels in here. I have to get a list of those, the coordinates of where they are. So you do that by, in the command prompt, you go find underscore hot. No. Find space hot. Like that. And then like 500. Wait, that's not it. I had it right the first time. Find hot COSM 500. Right there. Hot pixels detected 71. And you can run this number, the 500, anywhere from 2,000 to 500 or to 4,000. You want to do it until you have a rough, good number for the number of hot pixels that are in your image. I think that might be a little bit high. So I think if I decrease it, that number. Oh wait, no. If I decrease it, that goes too many. So I want to go find hot COSM. We're gonna go 2,000 now. Whoops. See, I forgot a 0, so I didn't like that. So I'll just copy and paste it. Add a 0. Okay, this time it found 19. I think that's a little closer to what's actually in the picture here. So I like that. So it wrote out a file that has those 19 hot pixels in it. You have to do that. And then now you can save your master dark. Dark ma, which is master dark, right? Okay. So now we have, we already made our flat because we saved out master flat, remember? We made an offset, which were both faked, and then we did a dark from actual dark frames. Now that we have those 3 files, we can go through and calibrate the light frames that we have, that we chose out of that directory every 5th frame. So we're going to do that right now. Digital photo, preprocessing. And under here, sorry about that. We're going to go, we called our light frame C, if you recall, right? Dark master, uncheck optimize, flat master. COSM is the file that it wrote out. And if you look in your working directory, you'll see it in there. See that? When you ran that find hot COSM command, it wrote this file out. So it needs that here for the calibration. And now that that's done, we're going to run into here and see if we can recall how many images we had. I had chosen 6, so C1 through 6 are the ones we're going to be calibrating. So we're going to call this 6, and we're going to call this CR for C registered, okay? And so what it's going to do is it's going to subtract the dark frames from the light frames to clean them up a little bit. That's, we're just registering and calibrating our images here. And so, yep, it's chewing through that right now. Hopefully that didn't give you a seizure. Let's see if we can adjust this. Okay, there's our actual image. If you go to this adjuster here and hit auto, it will load up your image for you, stretch it for you to a decent amount. And you can see here's NGC 772, and now it's been calibrated. Hopefully the hot pixels have all been removed. Now there's one last step. We got to align these images, which is very important for blinking. So that's under processing, stellar registration. And then we have, I'm going to choose global matching quadratic. because those two settings work very well. And so you can see it's actually writing out new FITS files every time we do this. So we started with the C1 through C6. Now we have the CR1 through CR6. So these are the registered ones, or I should say calibrated. They haven't been registered yet. And now we're going to register them. So I'm going to call the input name CR, because those are the ones that are calibrated, and the output name CRR, and the number again is 6, global matching. Okay. So now what we're doing is we're aligning the images. And so I wish I wouldn't have stretched it because it would preview this a little better. You can see what it was doing. So it finds all the stars in the image and then runs it through algorithms to align each image very closely to one another. So you can then blink them and take highly detailed measurements of any moving objects you find. The only reason it's showing up white is because I hit auto on the dark frame and it saved that setting. So if I hit auto again, it's going to bring my image back for me. And so we can look into the working directory here for our new images. There they are, CRR123456, which means they have all been registered, which is pretty cool. So right now I'm going to take a little bit of a break from the direction I was going to go, and just show you some other functionality that Iris has. I was going to blink my images, which is kind of flashing through the images quickly to look for moving objects in Astrometrica. But I just want to show you that Iris has the same functionality as well, which is pretty cool. So if you go into the command line in Iris, you run the blink to command, and then I want to blink every other image because I have 6 of them, 1, 3, and 6. Okay. So blink 2, CRR1, CRR2, CRR3, CRR6. Then the delay in milliseconds, I found 300 works rather well. Hit enter. I messed something up here. Oh, that says blind, not blink. BLINK2, CRR1, CRR3, CRR6. And 300 milliseconds. And again, it's white because it is auto stretching it wrong. Okay, now it's all stretched right under the threshold settings here by hitting auto, and you can control this manually. You can pull it back to really stretch it, and get a background in there a little more with these sliders. So what is this doing now? This is flashing the images at us over the course of the night, 3 of them at a pretty quick interval, looking for anything that might be moving around. And you can immediately see right here in the bottom, look at that thing cruising by there. Boom, there's definitely an asteroid in this set of images. And that's exactly what you're looking for. They're not always going to be this prominent and bright and easy to see, but right here at the bottom, boom, there's an asteroid flying through my pictures. So, and you know what's nice is that we don't have the hot pixels because we calibrated our frames. And we don't have, and they're all aligned because we registered them. If they're not aligned, they might be moving around between blinks, and that gets very convoluted when you're trying to spot moving objects. You want the stars to be laid right on top of each other in each image as it's blinking, and then you get a really nice shot at anything that's moving around. So you can see we got an asteroid in this shot, which I already knew. I'm just using this for the tutorial purposes, obviously. But so now what we're going to do is we're going to bring this into Astrometrica, plate solve it, and then take some measurements on this asteroid to see if we can identify it, now that we found it in the images. Alright, so now that we got those images ready to go, what we're going to do now is pop over into Astrometrica. So, this piece of software is a little hard to get acquainted with, but hopefully after we're messing around with this tutorial here, you'll be able to pick it up a little quicker than I did. It took me a while. So what we got here is, first thing you want to do is go to Internet and download the Minor Planet Center's orbital database. You have to do this once, and then you can update it from there on out. It's about 150 megabytes of information, and it has all the known objects flying around out there that you might encounter in your images. And then, of course, you can update it after you've downloaded it once. Then we also need to go into the settings. This is where things get a little confusing. So you pop this thing open over here with the wrench icon, and you start filling this stuff out, okay? If you're wondering where I live, there's my coordinates. Oh well. MPC code. This is a code that you will get from the Minor Planet Center. You're going to put all X's in here until they assign you one. There's a process you have to go through before you can get that code. And then, longitude and latitude of your observatory go in here. Your height, elevation goes in here. Name, email, and telescope information is going to go in here. How I express this here is in meters. So I have a 304 millimeter telescope, which is 0.304 meters, f4 reflector plus CCD. It's pretty much the information they want to know here. Now you're going to go into the next CCD panel here, and you're going to fill this information out with the telescope you were using. So the one I used has a focal length of 1,220 millimeters. 1,220 meters would have been kind of big. Now this is just millimeters, and then plus or minus 1% of that. Position angle, just leave this at 0 for now. If you know exactly what that is, great. But we're going to plate solve the images, and so the position angle we can determine later when we're solving the images. So I tend to just leave that at 0. The pointing, I just leave this at 5. Not sure why. That's how it came. I may have tweaked it a little bit. You can mess with that number if you have a hard time solving your images. You can flip your images horizontal or vertical when you import the star databases. Some of these options, I don't even know what they do. Autosave fits with WCS. No, I did. That's checked. That's how it was. It's working, whatever. Time in file header. Okay, so like I said earlier, I was shooting fits with Sequence Generator Pro, and it writes the time of my files right into the header. So the time it uses is actually the start of the exposure. And then it gives me the duration of the exposure in seconds, which you can see down here. The exposure from fits for my camera and Sequence Generator is measured in seconds, not minutes or milliseconds. And it starts with the time of the start of the exposure. This is very important because when you load your image, it's going to load the time for the image as the center of the exposure time, the middle of the exposure. It's not going to load it as the start or the end. It's going to load it as the middle of your exposure for when the object was in any given point. The CCD chip I'm using, I looked up online to find out what the exact pixel size of the ATIC 414EX monochrome was. You can do this for any other CCD you might be using. This one is 6.5 nanometers. So you just pop in the pixel width and pixel height right in these two boxes here. If you're shooting with a 16-bit camera, which is pretty typical, your saturation limit is going to be I believe this is ADUs, which is going to be 60,000 ADUs. Pretty typical. That's probably what you're going to be getting. Color band visual, again, the exposure from fits is in milliseconds. So we're just running over this. Now the program, I haven't messed with this too much. The object detection, this is pretty much for the stars in your image when it pulls all the stars out to compare them against the database. I think the default for this was 7. Just leave this to all the defaults before you get started tweaking it. I think I barely tweaked a few of the values, not even knowing what I was doing, so I'm pretty sure the default values are fine. Again, don't mess with any of these. Are all just default values. Don't mess with any of these. This is important though. The star catalog you're going to be using, which is a database that this thing ties into on the internet. Well, this UCAC database must be I can't remember. It was like 15 or 16 gigabytes of information. So this is not hosted locally on your machine. Astrometrica goes out to the internet to read this database based on the inputs you put into it when you try to plate solve your images. And they specifically say in the guide that I mentioned earlier from the Minor Planet Center to use the catalog UCAC4, which is a pretty accurate catalog. This is the magnitude, upper and lower limits that you're importing. You might have to tweak this depending on your setup. If you're picking up really small stars, what your field of view is. The defaults are a little different than this. I think it's 8 and 15. You can tweak this to get better plate solves though. The number of reference stars matching, 200, search radius 4. So again, you might have to tweak a few of these settings to get an optimal setup for what you're going for. But just play with them, don't be afraid to change some values and see if it works out for you. Environment, don't worry about this. I don't. It's just the colors and all that good stuff. These are the catalogs. Again, they're not locally hosted, so it's going to know where to go to find all this information. Viziar, it's another website that has these catalogs on it. And then for the internet, when you're ready to send off your reports to the Minor Planet Center, this is the settings you can use for an email server if you're going to be emailing your observations off. And they talk about that also in the guide. You have to send them off in a very specific format, and so make sure you're very acquainted with that. So I plugged in all my personal server information into here so I can send off the observations that I get. And so that's it. That's the settings. Woo! Okay, so now let's open up our images that we registered, and pop them into Astrometrica. So it's going to default to the tutorials, whatever. Go to the desktop. My working directory is IrisW. And again, here's all the images that we outputted in Iris earlier. I'm going to go with the CRR1, which is the registered and calibrated, to CRR6, which is registered and calibrated. And then, so, one important piece of information we need before we solve these images is not only what time they were taken, but where they are taken in right ascension and declination. So again, because the software I'm using writes the time information to my FITS headers, it picks that up automatically. I don't think that a DSLR is going to do this, so you're going to have to look in your DSLR files. You'll find the start of your exposure, the exact date and time, and then you're going to have to calculate how many seconds the exposure was, and then find the midpoint of that exposure, and that's what it wants right here, time, mid, exposure, UT. So you're going to have to find a way to determine the exact time of the midpoint of your exposure of your DSLR image. Again, it's automatically doing this for me, and I've double checked it. It's accurate with the software I was using. So at this step, all I have to do is just hit OK, because the times are correct. So these are my 6 images that I pulled out of that imaging session, and they're ready to rock and roll. So the next step we have to do is we have to plate solve this image so Astrometrica knows exactly where we are in the night sky. One way we can do this is go over to astrometry.net, choose one of these images, and upload it to their server, and let them plate solve the image for us, and they'll give us a lot of good information here. But it doesn't always work, so it's good to know how to do it the other way as well. So it's uploading, it's 18%, 19%, so you gotta wait for this thing to upload and then plate solve. The Simbad database is telling me right here that the coordinates, the J2000 coordinates, are 159.19.5. So I'm gonna click on this little icon here for astrometric data reduction. Okay, and so what does it want to know? These are objects you can import for like asteroids that might be in the database that you downloaded. But I'm not going to try and find my field of view based on the object. I'm going to do it from the right ascension and declination, and I'm in the northern hemisphere. So 159.19 right ascension, 01 59 19.5 if I recall. And then the declination is 19:00:27. So that's should be the coordinates for NGC 772. So what happens now is if I hit OK, it's going to run out to the UCAC4 database, look at the pixel size and the focal length of my telescope, and download the region of that database that should contain the stars that are in my image. But again, we have an issue because the stars in my image might not be matched up exactly north-south with the stars in the database because my camera might have been twisted a little bit. So I don't know exactly what angle I was shooting at in my images, and so we're going to get an error. Okay, so we have a reference star match error. And I got hung up here for a while before I realized that you can do this manually pretty easy. So the manual reference match is what we're going to go with here. Okay? And so what do we have? We have it load where it thinks the stars should be, which are all these red circles. And then, you know, they don't match at all with my image because my image is probably not centered perfect. And, you know, the stars in my image is probably twisted or flipped some way. So what you have to do at this point is figure out what angle you were shooting at to match up these stars. Now, I'm showing all the way up to a magnitude 17 star. That's pretty faint. The easiest way to match up is to look at some of the brighter ones. So I'm going to click this down arrow to get to like 14.5. And then I'm going to look for patterns in what I'm looking at with these stars. So like there's 2 stars right here that are pretty close together. Let's see. I should be able to pick out these 2 stars pretty easily with these 2 here paired up. So I'm just going to start plugging in position angles here in increments of 50, okay? So there's 50, that doesn't look right. I'm not seeing anything coming close to matching there. 100. And bam. If you look carefully at what I just did there, you can see that 100 is pretty close. There's 2 stars here. You can barely make out the other one there, so you can kick it over with the arrows. See that? I'm clicking the arrow over, and you can see that some of these stars are actually starting to match up. I got, just based on a guess of 100 position angle, I have 1, 2, 3 stars here that line up pretty good. You can see these 2 are almost lined up, and these 2 right here obviously go right here. So now I'm like, okay, now I know where I'm at. So now if you just hold the arrow button down on the angle, you can see I went the wrong way. Now it's at 98, they went further out of whack. So I'm going to increase it, and I'm just going to keep doing that until these stars line up much more closely to what's going on in my image here. So you can see the angle's just about right now. I can go ahead and click the down arrow to move the stars back closer into position. And because I had that right ascension and declination coordinates, I went too far on the rotation there. I was able to get in the right ballpark, and then I was able to drop the magnitude down to look at where the stars are in my image versus where the stars in the database that I imported were. And you can see now that I'm able to tell the software that my position angle is about 105 degrees. So if we look at Astrometry.net, it says, yay, I was able to solve this image you uploaded. So we're going to go to the results page, and I'm going to show you that that the right ascension and declination are given to you, and your degrees, your orientation is given to you as well. So that can put you in the ballpark. Of course, it's going to be different because it actually, I think it flipped the image. I'm not sure exactly why it's not showing that, similar to what I brought in here. The point is, you want to get the database that you import to match up with the stars in your image. And so the settings profile is very important as far as your pixel size and your focal ratio and all that stuff. Your focal length, you got to make sure you get all that stuff imported in correctly. Then when you go to plate solve, by clicking this button up here, you need to make sure you type in the right ascension and declination of your imaging area correctly. And so I actually started recording this information the night I shoot. When I click in my Planetarium to go shoot an object, I write down the coordinates for it. So later when I go to do this process, it's a little quicker. And so here we are. The image is ready to be plate solved. I've got the model matched up with my actual image. I'm just going to hit OK. And this is what you want to see. You want to see a lot of green stars. And so we have a lot of reference stars. It did a pretty solid job plate solving the image. So now all of the images in the entire sequence are plate solved. So that's step number 1. Very important to get that done. Now let's move forward here. So at this point, you want to shoot. You want to blink the images again to look for moving targets. Okay. So we're going to go images, tools, and then blink images, and then it's going to go through all the 6 images and start flashing them similar to what we did in Iris, but it actually works a little better in Astrometrica. I like their blink engine because it, even though the exposures might have a brighter background in some points or a little darker at other areas, if the moon had been setting or something, it seems to stretch the brightness pretty close between each of the images, which makes it easier to spot moving targets. And so if you look carefully here, you can actually see I have another little asteroid moving through this image right here. There he is. 1, 2, 3, 4, 5, 6. And a good way to know whether or not you actually have a moving object is when you choose your images, like I did out of my set for the night in my luminance channel. I chose them all at the same increment, so they were all 5 minutes apart. So if you have a moving object in your images, the skips should be an equal distance between each image. If you chose your images sequentially, with the same gap between each image, and it makes it easier to spot these little teeny moving objects in your images. Here's the asteroid we were looking at earlier. It's flipped the image, and so there's an asteroid here flying through my pictures. How cool is that? And so now what I'm going to do is I'm going to hit the stop button up here, and you can actually work through these frames individually with their little toolbar, which is also awesome. And so now I'm going to go find a nice frame. This one looks pretty good. The seeing was nice, the tracking was nice, and I'm going to click on this object to make a measurement of the object. There it is. And so it detects the brightness of the object flying in the frame, and this, actually I'm getting ahead of myself. We don't want to do a measurement yet. Well, once you download the MPC orbital database, what you can do at this point is under tools, you want to show known objects, known object overlay. And what this is going to do is it's going to look through the times that your image was taken, and now that it plate solved it, it knows exactly where it was taken, and it's going to compare that against the orbital database to look for objects that have already been previously discovered that happen to be flying through your field of view at that time. So this takes a few seconds here for it to analyze your image and look for all the known objects in this area. And boom. So we have a identifier for our object here. Now there's supposed to be another one here. I'm assuming that either the database needs better measurements because it's not showing up in the right spot, or it's possible that it's so faint my 12-inch f4 telescope was not able to detect it. But you can see how accurate my plate solve was, because every frame this object is right in the center of that little box. And that's what you want to see. That means your time is accurate, and that means your plate solve is accurate. And that also means this is not a new asteroid. We know what this is here. And so, you know, if you want to now take some measurements of this known object to report to the Minor Planet Center, this is how you do it. You just find the frame you want, you click on it, you make sure it's centered perfectly in the little circle here. And then if it's already a previously known object, if you click on this little button here for the object designation, you can see that 2001 QJ226, which is already in the database, is right ascension and declination 0000 from this location, which means it's directly on top of our object. This is our object. And you hit OK, and so that's our first measurement, and we hit accept. Then we skip forward 2 frames, do the same thing. Make sure it's centered. Select it. Object again is 0. JQ226 is 0 and 0 away from this location, which means that's it. Hit accept. And then skip forward again 2 frames. Click on the object. Load it up again. There it is again. Again, it's 0, 0. I mean, this means we're accurate. And hit OK and accept. And so we have measurements now. If we go to File, View the report file, you can see that this contains all of the information that we need to send to the Minor Planet Center. Okay, it built it for us, which is really cool. Now you need to read through their instructions carefully before you send them anything, because the first time you send them information, they want some more comm lines and some more con lines for their database. But pretty much what we just did is we took detailed measurements of J3895 in their database at 2015, 2011, 2015 on the 11th month and 15th day. So this is actually the day. This is measured instead of 24 hours. It's measured instead of minutes and seconds, it's measured in decimal points. So this is November 15th, 2015 in decimal points, and these are the exact times, universal time that this object, that we measured it. And then this is the right ascension coordinates at that exact time, and this is the declination coordinates at this exact time. This is the estimated magnitude from the software, and this is my observatory code, which again you're not going to have until they accept some observations and assign you an observatory code. So that's what all this means, and that's how you can take detailed measurements using Astrometrica of objects flying around in your images after you plate solve them. And of course, again, this little teeny faint object I was pointing out that is perfectly centered in this square is also a previously known asteroid. So we could go through the same process to make some measurements of it. Load it up, and it will tell us exactly what it is. 0 seconds away and 0 in right ascension and declination from this point is target 2004 EK91, packed as Z7466. These are all just designations for the thousands and thousands of asteroids and comets that they're finding out there. But that's our one. It's previously discovered. So you can take measurements of that. And again, here's another one with nothing in it. This could be two things. It's too faint for my telescope, or they need better measurements. So they encourage you to submit measurements of previously known objects that you find, so they can, once you've been accepted, they can refine the orbits in their database, and you can update your database and get more accurate information coming in. So that is how we plate solve, and take highly accurate measurements out of your images of asteroids and comets that and minor planets that might be flying around in there. Next, what I'm going to show you how to do is we're going to pretend like this asteroid was previously unknown. We're going to use the information that we saved in our report file to generate its orbit with find orb and import it into Stellarium, and so we could find it again at a later point in time. So that's the last phase here of the tutorial. Okay, now that we have our measurements all done, we want to view the report file and pull out the coordinates for our object. So what we're going to do is we're going to pretend like this is actually not a known object, even though it is a known object. And so say you're going through a set of images that you took and they were 3 nights ago or a month ago, and you want to try and relocate this object because it didn't come up in any known databases. And so how are we going to know if it's known from a database? Well, the first thing we can do is get the coordinates for it, the C from the name over to the time to the right ascension and declination. And of course, if it didn't come up in Astrometrica, another check we can do, obviously that one did, but if it didn't, you would go to the Minor Planet Center's website again, go under Observers, and then the other observer services, and then the MP checker. And then we're going to just copy the stuff here for reference. And then so we have C, we can just delete that, 2015-11. Okay, and then the universal time we're looking for, and then again this is the day, so this is obviously, the hour, this is 2300, so we're gonna update that to 1500 because that was our observation from Astrometrica. And then we're gonna take the right ascension and plug it in here, and then the declination with the plus sign and plug it in here, and then we're gonna say at this area, this J2000 position at this exact date and time, look in a 15 arc minute radius for any known objects. So produce list. And it's going to run this information against their database and say, oh, I found this object in the area where you put your information, or I didn't find any objects. And of course it came up with quite a few different objects, one of which is the object that we already identified from Astrometrica, which is obviously the first one at the top of the list here, which was 2001 QJ226, which we already knew. And it also tells us, okay, we don't need any more measurements at this time for this object. And yeah, so here we go. This is a pretty accurate measurement here. So that's one way you can check for objects that are previously known, if you took a measurement of an object in your images and you weren't sure if it was previously known. So we're going to pretend like nothing came up here, and it's a new object, and we need to find it again. So how do we do that? Well, we're going to copy this information into a new text document. we're going to change the COD, which is the observatory code, to 500 because that's geocentric, which means we don't have an observatory code, so we're pretending like we're in the middle of the Earth. And it will understand that. So save it, and then fire up Find Orb. And once we do that, we're going to click on Open. You have to do this twice because there's a bug in the system. And then run over to our new text document. And ta-da! It outputs orbital elements that we need to input this information into Stellarium. Okay? So we're going to save to clipboard, copy to clipboard, run into our text document, which actually should already be open. No, it wasn't. Okay. So we're going to paste that information in here. Then we're going to go get the format that we need for Stellarium. Okay, so here we go. This is the format that Stellarium needs to understand, okay, what is this object we're going to import? What are the values for its orbit? Okay, so the M, well, the first thing we need is the Julian date out of the line up here that comes after this area, 2015 November TTT. The JDT, I think it's the Julian date time. We're going to go down here and paste that onto the first line here. And then we're going to run into the semi-major axis. Which one is that? That's, I think it's this one. The A up here. And then we're going to run into the eccentricity, which is the E. That came out of Find Orb. The inclination is right here. So I'm just copying and pasting these values down here. The ascending node is right here. The pericenter is right here. And finally, the mean anomaly is this M up here. So bam, we have all the values we need now for the orbit of this unknown Rankin. You can name this anything you want. Okay, so 002 Rankin, whatever. We'll call it UNK1, unknown 1. Of course, you can just copy and paste that right down to the next line. It orbits the sun. And then we're going to take all this information. You're going to run into Stellarium. You have to make sure that under settings, under plugins, that you have enabled the solar system editor and load it startup and then restart. What this does is it creates a file that you need to get to edit. And that file is located at C, users, David, app data, roaming, Stellarium, data. And it's called the SS system INI. We're going to run in there and we're going to paste our new object and save it, okay, into that file. Okay, so we're going to load all this information into the SS system INI file, save it, okay, and we're going to close that out and then relaunch Stellarium. And I have already imported that asteroid into the database. I'll show you how to do that too. But we're just going to go search for unknown 1, okay, and now we have an element in Stellarium called unknown 1. And this is the rough measurements from our images that put it right here in Stellarium, based on the observations we got from Astrometrica and the orbital solve we solved from Find Orb. And now we're going to see where it thinks the actual asteroid is, which I already loaded. And the way you do this is you go into your designation here, J3895, and after you load the solar system editor, you can run into scripts, solar system editor, configure, solar system, import orbital elements in MPC format, and then you can look for asteroids, search online, type it in there, hit search, it comes up, and then you're going to say add objects. And that's all there is to it. Close all that out. And now it's in our database. So here's unknown 1 based on our our solve of the orbit, and then we're going to load up now 2001 QJ226. Okay, so the idea here is that we have this unknown object we found flying around in our images. We only got 3 observations on it, so not enough data to really solve a meaningful orbit. But was it really enough? That's the question, right? So here I'm going to load up the field of view that my CCD has. And this is actually a very narrow field of view. I'm shooting with a very small sensor on a very large scope. And so I'm covering a pretty small area of the sky here. And I want you to notice that the unknown object that we imported and created based on those 3 observations that we took in Astrometrica and generated an orbit for is pretty darn close to our comet, our object that we're after, which is right here. And so you can see that's the actual comet that is well known from the database. And here's the object we were able to measure through our images, generate an orbit for, and import into Stellarium. It put it on the sensor, which is pretty amazing. So had this been those dates were the 11th of November. Right now it's the 23rd. So even after all that time, I was able to extract enough information where I could go out tonight, and had I used this coordinate, it would still be close enough where it would put this object back in my sensor field of view based on the information that we imported directly from the Minor Planet Center's database for that object. So had this been a new object, I would have been able to relocate it again tonight. And that's the idea, is being able to find something in your images, go back to it, find it again, get more in-depth, detailed observations, and then submit those off. And so hopefully that will help you get a better idea of how this all works. And if you have any questions, feel free to post them in the comments. See you later.